Does this reach over here by chance?
Yeah, it does.
Cool. Great.
I just leave the iPad to be plugged always because it doesn't have enough battery.
Yeah, keep it plugged. Perfect. Are we recording?
Yeah.
Okay.
No,
All right. Welcome back to a tour of topology, as usual. Let me tell you what we were talking about last time. Talking about Rn. What's Rn? Well, so it's the natural generalization of all the things that we had seen in two special cases where n is equal to 1 and n is equal to 2. So, as a set, Rn is the set of all ordered n tuples of real numbers. So the word ordered means, so here's the notation I'll use. If x is a point or an element of Rn, I'll always use x1, x2, etc. as the components, called the components of the coordinates of the point x. So we should realize that when we say x is equal to y, we mean that each xi is equal to yi. Okay, so Rn is what's called n-dimensional Euclidean space. Okay, so that word Euclidean that comes from geometry. We've also been using in our discussions of topology as well. So, so when n is equal to 1, well, R1, which usually we just call R, so that's our line. When n is equal to 2, we have R2, which is the Euclidean plane we had been talking about a lot. So, for example, when n is 3, well, we also have something that we've talked about as well, but not too precisely up until this point. So R3, three-dimensional Euclidean space, is, well, it's a mathematical model of the three-dimensional space that we live and breathe in. So we can do this with Rn for any n. Some of the important things about Rn, if I have two elements of Rn, x and y, we talked about last time. In fact, moreover, if I have a real number, so-called alpha, then we discussed last time that we have x plus y, and we also have alpha times x, which are points in Rn. And in fact, we can call points in vectors Rn. We can call points in Rn vectors in Rn to satisfy the rules of the vector space we talked about last time. Moreover, there is the idea of the norm. So in fact, this is a generalization of the idea of absolute value that was important in the real numbers. And one way to define a norm on Rn is, so this is basically comes from the Pythagorean theorem. It generalizes both the absolute value on R as well as the norm that we had already been using, although we hadn't been calling it the norm, on R2. Comes from, this formula basically comes from the Pythagorean theorem. So I have the sum of all the squares of the coordinates of x, and then at the end I take the square root. So we mentioned how this allows us to define distance. In fact, I believe we had been using this notation for distance in R2. You can define distance between points or vectors in Rn in this way, simply as the norm of x minus y. It generalizes the distance formula that we all learned in analytic geometry, in multivariable calculus. What's this x minus y, by the way, in case we weren't sure. It means x plus minus y, which if you want means x plus. It's a useful fact to know this is the same as x plus the scalar minus 1 times y. So a kind of interesting thing here is that this works for every n. For every n where? For every natural number n, 1, 2, 3, 4, 5, etc. But it works as well if n is equal to infinity, as long as you learn how to think about this the right way. So in fact, r infinity, so I think last time I put a 0 down there, but then I also later realized this kind of is standard, at least in one textbook I know of. R infinity includes the condition that I gave you last time. So this is the set of all, you can call them vectors or points, or maybe sequence is a good word, infinite sequences, because in R infinity the list of numbers goes on forever. But we're going to add this condition that so for each point x, or each sequence x like this, that it's eventually 0. And what that means is, so to make that precise, that so eventually the sequence looks like 0, 0, 0, 0, 0, 0, 0. Perhaps after the first billion coordinates or something like that. So to make that precise, you can say that there exists in n, natural number n, such that x, let's say, yeah, x. So first of all, yeah, each xi is a real number, and there exists in n such that xi is equal to 0 for I greater than n. So it's the set of all sequences of real numbers like that, but they have to eventually be 0. But there's no limit to how many non-zero coordinates there are, as long as there's only finitely many. So in fact, the formula that I gave you for the norm works the same. The norm of this x is going to be the sum of x1 squared all the way down to xn squared in the square root. You only have to add up until you get to the rest of the coordinates being 0. It's actually the same formula for the norm and for the distance. So Rn, where n is a natural number, but it's fine if you include infinity as well, is what's called a metric space. More specifically, this is just terminology, it's not that important. More specifically, what's called a normed vector space. We discussed last time how any metric space is a topological space. T could be, so it's the topology on Rn generated by what we call open balls. So B, X, R means the open ball centered at X with radius R. So we define that just using the distance function. In fact, this topology works in any metric space. It doesn't even have to be Rn. So it's the set of all points P in Rn such that the distance from X to P is less than 1. So R can be any positive real number. X is, in fact, X can be any point in a metric space, really. We have a topology on that metric space. Okay. So yeah, I mean, we had seen this before. When n is 1, we're talking about our good old open bounded intervals. In fact, if this is x here, then this point over here is x plus r, this one is x minus r. When n is 2, we had been using the term open disk. So here I have a point x in R2. I take a circle with radius r, centered at x. And that's my my open ball is what we had been calling an open disk. You can still make a reasonable picture. In the case that n is 3, you have to draw a sphere. So if x is the center of the sphere with radius r, the open ball really is what we would call in everyday life a ball. It's all the points that are strictly inside the ball. The distance has to be less than r. So for example, this point here is actually not on the it's not a part of the set. Okay, so let's explore a concept for these spaces. In fact, here's a definition that makes sense. In any topological space, actually, we had kind of seen this concept before when we were talking about the real numbers, but I don't think we used this word or any of these words. So here X is any topological space. If I have a collection of open subsets of X, we call this an open cover of X. The word cover means that it comes from the everyday usage of the word. It means that the union of all of those open sets, which are subsets of X, is as big as possible, so it's actually equal to X. So an open cover of X is just a collection of open subsets of X whose union is X. So a cover could have finitely many sets, or it could have infinitely many sets. So it's finite. Well, almost nothing to say here. It's finite if the collection of open sets is finite. No surprise there. A subcover of this open cover of X is a it simply is a this is just getting down some words to talk about these things with having to use so many words. Is a collection of subsets in the open cover. Subcover of this open cover of X is a collection of subsets in the open cover. Well, that's also an open cover of X. So that means that the union of the union of those open sets is also equal to X. So those are just some words to get to this definition, to be able to state this definition in an efficient way. Definition: a topological space is compact. Compact if every open cover of X has a finite subcover. So in fact, we had seen this before, although I didn't introduce you to the word compact nor the word open cover, subcover, anything like that. So these are examples. Actually, these were previously mentioned examples. I'm going to put these examples in a broader context. So the typical compact space is the following subspace with the real numbers. It's a closed and bounded interval. So when we talked about the topology on the real numbers, I had mentioned that this is a type of interval, in fact the only type of interval in the real numbers that has a very special property. I didn't use the word, but that special property was compactness. So X is the closed interval, AB, so you have to remember this is the subspace topology. So X is given the subspace topology of the standard topology of R, standard or Euclidean topology of R. So this is an example of a compact space. So this is an example of a set where every open cover has a finite subcover. So whenever you can find a collection of, for example, open intervals whose union is this closed and bounded interval AB, you know that you can you can pick out only finitely many of those sets, and it still is a cover of X. That is actually difficult to prove. This will be a special case of a theorem that I'll give you in just a minute. So in fact, all other types all other types of intervals in R are not compact, which is just as useful to know that. So for example, an open and bounded interval, AB. Here's an open unbounded interval. So is this. An open unbounded interval. You have closed and unbounded intervals. Then you even have ones that are neither open nor closed, that look like this. So here you include A but not B. Here you include B but not A. And in fact, the one interval, the one non-empty, so actually we should say all other types of non-empty. If you want to call me out on the empty set, you probably could. All other types of non-empty intervals in R are not compact. The one type of non-empty interval that's both open and closed is the set of real numbers. That's not compact. So R minus infinity, that's also not compact. Okay, we had discussed this before. I'll repeat the example I gave to think about again. So for example, actually here's a couple examples. Here's a good example to know. So if I take the union over all rational numbers, in fact, if I just take the open interval from x to x plus epsilon, here epsilon is any positive number. This, in fact, is an open cover of the real numbers. This is using the fact that we mentioned earlier. So this is because of the fact that we mentioned earlier that Q is dense in R. although it's not difficult to see. So in fact, this works for any epsilon greater than 0. That's why Q is dense. But it's not difficult to see. In fact, it's pretty trivial that there's no finite subcover of this cover. There's no finite subcover. So R is not compact, non-compact. You could think of lots and lots and lots of open covers of R that have no finite subcovers. In fact, ones that are easier to see than mine, but I liked mine because it reminds us that Q is dense. Here's another one. I think this is the one that I gave earlier. So let's take the union over the set of natural numbers of the interval from 1 over n to 1. This is an open cover of, so what's the picture here? Here's 0, 1. So for example, when n is 1, I have, well actually I have the empty set when n is 1. When n is 2, I have the interval, the open interval from 1/2 to 1. When n is 3, I have the interval from 1/3 to 1. When n is 4, I have the interval from 1/4 to 1. So if I take the union over all n, I have a collection of infinitely many open sets. I get an open cover of the open interval 0, 1. Once again, it's not difficult to see that this has no finite subcover. So the open interval 0, 1 is not compact. So the question, well, I told you without really justifying that the closed and bounded interval AB is a compact subset or subspace, if you want, of R. So, question or problem, what are the compact subsets, subspaces? To remind us of the subspace topology would be a good idea. So what are the compact subspaces of Rn? So we'll give an answer to this question in a moment. So in fact, it's kind of easy to see when it's easier to see when a set is not compact. So let's try and think of some things that. Let's think of some things that a compact space, some properties a compact space would have to possess. Here's one. So this definition actually is any metric space. XD, any metric space. So we actually had been using this word for the real numbers, bounded intervals and unbounded intervals. What does it mean for a set in a metric space to be bounded? So Y to subset of X is bounded. And this definition uses the metric in an essential way. This does not make any sense whatsoever in a topological space where you don't have a metric. It's bounded if, well, we can say it pretty simply. It's bounded if, using the notion of an open ball, simply if there exists an open ball in X that contains Y. Very simply stated like that. Otherwise, Y is unbounded. So, for example, well, we had already been using this terminology, in fact. So bounded intervals in R. So those are all the ones that would look like this. Here's open, here's closed, and here is semi-open, or half-open, however you want to say. Those are bounded intervals in R, and they're bounded according to this definition of boundedness in any metric space. So, if you have any interval, whether or not you include one or both endpoints, doesn't matter. So you can always find a larger open interval that contains them. Okay? All other intervals are unbounded. As we've been using that terminology. So in an interval that looks like this, it goes forever. To the right is unbounded because you just simply cannot find a open interval that's large enough, a bounded open interval. So a bounded open interval is an open ball in R, and you simply cannot find one large enough that contains the entire set. Okay, how about in R2? So we had seen some special subsets of R2. Well, lines, when we just talk about lines, those are unbounded. Just like the set of real numbers. Line segments, which are a lot like closed and bounded intervals, those are bounded. We had also talked about the conic sections. So which conic sections are bounded? Well, that's easy to see based on our pictures at least. Ellipses are bounded. Here's an ellipse. Can I find an open ball, which in this case is an open disk that contains my ellipse? Well, sure, I just have to look big enough. Ellipses are bounded. I think, though, that the other conic sections are unbounded. Parabolas and hyperbolas are unbounded. Parabola. You just simply can't find an open disk big enough to contain the whole thing. In fact, let's go back to the ellipse. So here's an intuitive notion. It's hard to make this, well, no, in this one example, it's easy to see. So you have the inside of an ellipse. I mean, this, you can include the ellipse itself if you want, it doesn't even matter. The inside of the ellipse is bounded, whereas the outside is unbounded. Yes? Actually, believe it or not, this is an important idea in topology, and the idea of the inside and the outside of a curve, such as an ellipse. In fact, this goes back to something that we had seen early on, before all this fancy stuff with topological spaces, when we were just talking about graph theory. So if let's say G is a finite plane graph, So it's a subset of R2. For my space X, I want to think of the complement. We had discussed that again recently. So I want to think of R2 minus the graph. We had recently discussed the connected components of the complement of a finite graph, which you'll remember goes back to our discussion of the Euler characteristic. So its connected components are, what do you think? Are they bounded? Are they unbounded? Well, here, let me write the sentence. Its connected components are bounded, but I'm not done yet, except for one. We had seen this in pictures during our discussion of graph theory early on. So just make whatever finite plane graph you want. So we have 1, 2, 3, 4, 5, and 6. So 1, 2, 3, 4, and 5. Those connected components of the complement of my graph are bounded subsets of R2. But 6 is unbounded. This would be a very difficult thing to prove, actually, I think. Okay, so why are we talking about boundedness? We were talking about compactness a minute ago. Well, the fact of the matter, and this is not difficult to see, it's not difficult to see that compact, so compact where? Not in any topological space, but in a metric space. Compact subspace of, well, I would just say compact metric space. Well, maybe it's good to say it that way. Compact in a metric space implies bounded. Oops. Or if you want to say it this way, unbounded implies non-compact. Actually, this is really easy to see. Take a point, P and X. You just have to think of the right way to explain it, and then it's easy to see why that works. If I take any point, P in a topological space X, I can take the union over the natural numbers of open balls centered at P with radius n. So as n gets larger and larger and larger, that union is going to contain every point in X, if you think about it. So this is an open cover. Of X. So, well, from there you can see that because of that fact, that if X is compact, it also has to be bounded. Otherwise, you would have an open cover without a finite subcover. Okay, so we would just know that compact always implies bounded. If it's compact in the metric space, it has to be bounded. In fact, another little observation, it's a little, so a bit less apparent, a bit less apparently, is that compact, once again, in a metric space, got to be careful here, implies something else. This won't be surprising if you look at our examples, compact set. So what happened in R? Which intervals were compact? Well, they had to be bounded, and they had to be closed. So sure enough, in any metric space, compact implies closed. Those things are not too difficult to see. So yeah, if you wanted to think about that, I mean, so if you have a set that's not closed, so here's a limit point. Limit point of x. So you have to think about how, if it's not closed, so there's a limit point of x that doesn't belong to x, then you can find an open cover without a finite subcover. In fact, that's a lot like the example we just did with 0, 1. You can do the same thing, actually. You can open cover of this space. It doesn't include that point without any finite subcover. So if it's compact, it would have to include all of its limit points. So, in any metric space, compact, so you see compact is a very restrictive condition. A compact subspace of a metric space has to be closed and bounded. So, of course, the question should be, what about the other direction? If I have a subset of a metric space that's closed and it's bounded, do I also know that it has to be compact? Well, that would be nice. Before we get to that, here's an extremely famous theorem in mathematics called the Heine-Borel theorem. So what this theorem says is that arrow facing the other way with the question mark, the answer is yes in Rn. So it's extremely useful, beautiful theorem. X is a subset of Rn. I've got to be careful here. Remember the whole business with infinity. And it's a natural number, so if you want it n is less than infinity, it's a natural number. X is compact. So again, remember the definition for that. It's kind of complicated. It's a definition you have to think about a lot to get used to. Every open cover of X has a finite subcover. If, and only if, well, X is closed and bounded. So determining the compact subsets of Rn, where n is a natural number, is actually really easy, according to this theorem. This theorem is a deep theorem. So included in this would be our special statement that, so a closed and bounded interval, AB, and the real numbers is compact. So that would be a special case of this. Even that is kind of difficult to prove. So for instance, in fact, this is a generalization of that example. I take an open ball, let's say centered at P with radius R. Well, first of all, this is an open set. It's not closed. It's not compact. But if I take the closure, I talked about this earlier, well, at least for R and for R2, the closure of an open ball is what's called a closed ball. So what it is the set of all X in Rn such that the distance from P to X is less than or equal to R. So it's closed. It's not too difficult to see it's closed. It's even less difficult to see that it's bounded. So this is compact according to the Heine-Borel theorem. In fact, the boundary actually really is called the boundary. If you take that closed ball that I call it a closed, this is a closed ball. If you take the closed ball and you take away the open ball, which is called the interior, you get what's called the boundary. It's the set of all X and Rn such that the distance from, what did I call it P before? Yeah. P. So take away the set of all points in Rn such that the distance from X to P. Well, okay, so if you take away the open ball, you get the points where the distance is exactly equal to R. This is compact too. So, in fact, well, if n is 1, you're in fact talking about 2 points. If n is 2, you're talking about a circle. N is 3, you're talking about a sphere, etc. Those are also compact. You can use the Heine-Borel theorem to show that they're certainly bounded. You just have to show that they're closed, and then you know that they're compact. Okay, so I mean, some other things worth noting based on this finite union. So what do we know about closed sets? The finite union of any collection of closed sets is closed. Infinite, no, not necessarily, but always works for finite. So a finite union, for example, a finite union of closed balls. Well, is it closed? Yeah. Is it bounded? Yeah. There's something to show there, but it is also bounded. So a finite union of closed balls in Rn. Oops. It's compact. Once again, remember, n is a natural number. Don't get carried away with infinity, but yeah. It's compact. So one of our earliest examples of a topological space, finite graph. Finite graph in R2, a plane graph. It's compact. In fact, once you know that line segments are compact, then you can see that a finite graph is compact. In fact, a line segment, well, a line segment in R, a closed interval, is a closed ball. But yeah, in R2, it's also closed. Okay, so in fact, yeah, a finite union of closed balls in Rn is compact. In fact, a finite union closed balls or any, let me squeeze this in here, any compact sets. And that generalizes immediately. If I have a finite collection of compact sets, so they're closed and bounded, so the union is also going to be closed and bounded, so it's compact. Take finite unions, compact sets, still compact. Okay, so yeah, finite graphs in R2 are compact. We had, shortly after studying graphs, we had mentioned the polyhedra. For example, a convex polyhedron in R3 is an example of a compact subspace of R3. For example, one of the 5 platonic solids that we had discussed. Tetrahedron, cube, etc. Okay, we can add to this polygons. 2, take your favorite polygon. Number 2, going to be a compact subset of R2. Okay, so compact sets show up all the time. Closed and bounded subsets of R. Let's go back to, so let me introduce some notation here. X is in Rn. N is a natural number. Let me include now the possibility of infinity. Here is some, so I have, so remember, I'll denote the components of X by X1, X2, etc. So what you can do is you can think about so let's fix, let's say J. J is a fixed natural number. You could consider the vector with the following property. X, I is either equal to 1 or 0, and it's 1 if I is equal to J, it's 0 otherwise. So if I is not equal to J. So we denote this X by, this is a notation you might have seen in linear algebra, if you ever took that class. We denote this X by EJ. So EJ is the point in Rn where all the components are 0 except for the jth component, which is 1. So E1 looks like 1, 0, 0, etc. So, I mean, the list could stop or it could go on indefinitely. Notice it is an element of R infinity because it's eventually 0. E2 would be 0, 1, 0, 0, etc. E3 would be 0, 0, 1, 0, etc., etc. Okay? So this set of vectors, EI, where I is any natural number, this is what in linear algebra they call the standard basis. Standard basis. Rn. Well, I guess we should say something like if n is infinite, then EI is so actually what I'm really interested in is infinity case. You guys can modify this if you need to a little bit. So okay. n is 1, I'm just talking about 0, you have 1. I'm just talking about the number 1, if you think about it, just the number 1. And it helps sometimes to visualize things. We like to visualize vectors as arrows. So if you can visualize it as that arrow if you want. Oops, this is in. To 1, n is 2, talking about the plane, and my vector is e1. Here's e1 in this case. When n is 2, you're talking about e1 like this, e2 like this. N is 3, talking about maybe e1 like this, e2 like this, e3 like this. So what we're actually going to do is we're going to consider the space x equal to all of the EIs. Well, okay, so maybe let me clear up what I was trying to say earlier. So EI, actually, maybe the good way to say it is this. So I goes from 1, 2, 3 up to n. So up to n. Just a little more space. Hold on. Vectors EI. So I goes from 1, 2 up to n. So if n is equal to infinity, I'm saying that x is infinite. X is e1, e2, e3, it's infinite. And it's infinity. Okay, so we're actually going to, I just want to think about this topological space X. First thing I'll have us think about is what is the distance from EI to EJ. So we have to think carefully, what are we talking about? So those are our elements in Rn, elements of Rn. Rn is a metric space. So we're calculating the distance using the metric on Rn. So what is it? In fact, you can see in the first few examples, for example, in R2, what's the distance from, what's the length of this line here? You know from geometry. Yeah, so it works the same in R3 as well. Any of these distances here are going to be square root of 2. But you can just think in general, if I have two sequences where I have a 1 in two different positions, and I calculate the metric, I'm going to get the square root of 2. I get the square root of 2 if, well, as long as they're not the same, once again, I need a little more space here. So I get the square root of 2 if I is not equal to j. Well, if I is equal to j, we know what we have to get, because it's one of the rules of a metric space that if the distance between point and the same point is 0. Oops. So the distance is 0 if I is equal to j. Fine. So what does that mean Well, it means that as I use different values of I and j, those distances, well, they pretty much stay at the square root of 2 unless they're 0. In particular, this has the following consequence that, so if I take just the set containing EI, remember, so thinking of this as just a point in X, which was the set of all vectors like this, I think this is going to be open in that subspace. In fact, it's, so in fact, what it is it's the open ball centered at EI with radius R, and then I take the intersection with X. That's a true statement as long as R is less than or equal to the square root of 2. So this implies that this is open in X. So when you have an X where so if you have a space X where the set containing just one point is always open, that's called a discrete space. Remember? So X is discrete. Notice that, as we had mentioned earlier, it's finite if and only if n is finite. In fact, a finite subset of a metric space is always discrete. A finite subset of any metric space is discrete. An infinite subset of a metric space may or may not be discrete, but in our example, with the standard basis vectors for Rn, when n is infinite, it's actually still discrete. If you think about what discrete means, so if I have a discrete subspace, in fact of any space, a discrete subspace of any topological space is closed. That would actually be a good problem for those of you who are trying to learn this stuff. Why not? We'll call it a problem. A discrete subspace of any topological space is closed. So, and finally, so it's closed. Is it bounded? That's even easier to see. X is bounded. X is bounded. Well, since I mean all the distances were square root of 2 between points or 0. So, for example, the open ball centered at EI with radius R, in fact, contains the entire set X as long as R is big enough. In fact, as long as R is greater than the square root of 2. So what have we figured out here? Thus, X is closed and bounded in Rn. Hence, by the Heine-Borel theorem, X is compact. But you have to be careful. It's compact if n is less than infinity, because that theorem only applies to Rn and is finite. So, why are we talking about this? However, if you think of X as a subspace of R infinity, so X is an infinite set. It's an infinite discrete subset of a metric space. In fact, a discrete. Okay. The point is that the big punchline is this: this is not. In fact, if you want to continue your earlier problem, that any discrete subspace, the metric space is closed. A discrete space. A very nice, deceptively simple problem. A discrete subspace. A discrete space is compact if and only it's finite. So since we have an infinite discrete subset of a metric space, it can't be compact, but it is closed and bounded. So what this tells us is that the Heine-Borel theorem, it works in Rn, it works in finite dimensional Euclidean space, but it does not work in this R infinity, this infinite dimensional metric space. All right, we'll take 5. So how do you stop this thing? No.
Okay, we have taken 5.
All right.
Splendid.
que estudia Western, en el Western, prácticamente no hay nada más. ¿Qué significa no hay nada más? Todas tienen ese problema. Pero hay una que dice, este es el ranking y este no es el ranking. Entonces, ahora digamos que usted quiere ser pescador, tiene que existir escolas en otros. Porque ya sé que se van a decir. Nosotros también hacen en todas partes, pero ahí tienen 50 pescadores desde uno que es expertos. Entonces, aquí usted se gradúa de una más de un montón. Y el que está en la zona es cualquier cosa.
Es que por además yo estaba viendo las universidades y las zonas de orgánica y orgánica, y después de los años en la que me las se decidió que solo reducí mi lista a pocos, después yo entonces se me reduce aún más, porque casi poco. Se ve ahorita con el estrés que estoy, no voy a aguantarlo. No. Y en Francia ya me quedó súper muy ahorita con todo lo que estoy, es una nota de todas las clases. De verdad, si estoy en cuántica, ahorita ya perdí la carrera. Solo quiero con estas horas sí.
Y Ana, deje de joder, por Dios. Cierre la boca y no te escuche. Hay otras dependientes.
Eso es como la lista con topología.
Can we start in 3 minutes?
Yeah. So what do you think about what should we test for this partial?
I just started, no, I haven't even started the quiz.
Okay.
I was going to do that today. No, I didn't. I guess I just went in the game to see.
Okay.
Okay. So that's 6-4.
Right.
So I should finish up one day.
I would probably do. I wouldn't do Green's theorem. I don't think, because I didn't assign homework on it yet.
Well, that's the problem.
I assigned homework through the section before. Let's do this week.
That's what they have.
So 6.3 is the fundamental theorem for line integrals.
Right. And that's what I told my students for sure through 6-3. So I don't know, we'll see.
Do you want to do 6.4 or should we?
emociones que no do it on this text
In the
and
final.
we're saying then.
I know, I just thought about that too. Yeah, that's kind of where you draw the line with what's really important and not. There's the Stokes theorem and divergence theorem and all that. It's hard to squeeze that in to do it justice, but Green's theorem. But maybe we could, if we wanted, we could have like one question on the final partial credit, you know what I mean, for Green's theorem. I don't know, or just multiple choice, whatever.
I'm funny doing that. I mean, the homework. Tell them if they do it, and give them homework value and collective.
Sure.
That's the
Yeah,
problem.
that's true. That's true. You're right. We could include Green's theorem then. Maybe we should,
I would rather do that there, so we don't have to.
so we don't have to worry about it for the final. Yeah, sounds good. Ready when you are.
Push it to the breaking point.
What's that?
Push it to the breaking point.
These people?
All of them. No. I don't care. Okay. Push it. I don't know what
Can you
video.
get me? Do you know the password?
Okay. No, I don't. Heck. Oh, no. Okay.
No, yeah.
Need to get inside this thing.
You don't know the password?
No, she didn't tell me.
Oh, that's right. It ain't ours.
You know, I'm like, that was the hardest thing for me.
Yeah. Yeah, it's because the definition is complex. Actually, that's the whole point. Is that the definition the definition is complex, but it works out in reasonable spaces such as Rn. It's easy to understand. So yeah,
1996.
1996. That was a good year. I started high school that year.
I got divorced 1 year before 1990.
Sorry to hear that.
No, okay. So how do we?
Are we going?
Yeah.
Okay, so it's recording.
Yeah, but I don't know. I don't see the.
Yeah, do you know how to start up the? Whoa, let's try that. Wow, that's great.
This is insane. Tenemos problemas.
So when you say sub-collection, the open sets must be the same as the one from the original.
Yeah, so you have this big giant collection of open sets that cover X, and it's compact. Given that, you can always just choose finitely many of those
Change.
to still cover X. So it's never necessary to use an infinite collection of subsets to cover X. If you start with an infinite one, you can always reduce it to a finite subcollection. And that's what makes, so once you know that a space has that property, then you can do all sorts of nice stuff, because whenever you come up with an open cover, you can just say, now let's consider a finite subcover, and then you can.
Right. Yeah.
I'll give an example so the fact that you have maximum and minimum values of functions, for example, follows right from that.
Here's your share.